So the next thing we're going to talk about is the degree of a vertex. So we're going to talk about degrees. I'm not talking about like academic degrees. I'm talking about this thing we call a degree of a vertex. So let us consider the degree of a vertex. So I'm going to give you a definition and I'll give you an example. So here I think is a pretty good starting place. So I'll use one of the graphs I drew earlier. So I have A, B, C, F. I'm just adding those two edges in there. F, C, D, and E. So you might ask, what exactly is the degree of a vertex? So what does degree mean? So very often this is denoted as deg of V. So if I give you a vertex V, deg of V is the degree of the vertex. It is simply the number of incident edges of V, or on V. So for example, let's consider the degree of A. So how many incident edges are there on A? 1, 2, 3, 4, right? How about, let's consider the degree of, say, let's consider D. D's right here. How many incident edges are there on D? Let's see. Let's just count them. 1, 2, 3. There's 3 of them. Piece of cake, right? How about the degree of E? Can somebody tell me that? How many incident edges are there on E? So E's right there. Well, it's just 1, right? It's just 1. So this is what I encourage you to fill in the rest of the degrees of these. So that's what the degree is. You can also define on directed graphs or digraphs the notion of degree, which generalizes over it. So you have this concept of what we call the in degree and the out degree. The in degree is simply the number of incoming edges. So if you look at the arrows, they're pointing towards the vertex. The out degree is the number of outgoing or edges that are leaving. So so if you have your directed edge that goes from one vertex to the other, the outgoing edges are the ones, so if you look at the head of the arrow, the ones where they're not pointing towards it, so they're going outwards, the out degree counts the edges that are leaving a vertex. The in degree counts the ones going inwards, okay? So a natural question is there any relationship between the vertices, their degrees, and the edges? So this brings me to a cute but powerful result. So very cute but powerful result. So often this is called sometimes a degree sum formula, but I'll refer to it as the handshaking lemma. Though the handshaking lemma has a few different characterizations. And people call this the handshaking lemma for 2 reasons. First, a lemma is a theorem, but very often this is used to help you get to the main result. That's why it's called a lemma. Lemma is a special name for a theorem. Handshaking in the following sense. So suppose that maybe I'm at a party or something like that. Perhaps you probably get out more than I do. Suppose that this graph here represents the handshakes that were happening among people. So suppose that person A handshakes E, F, C, and B. you'd agree with me that from the perspective of A, how many handshakes happened? 4 of them happened, right? But if you ask E, how many handshakes did E partake in? 1 happened. There's 1 handshake that happened. Now, this relationship for what each one of the party members, people at the party, will tell you about the handshakes actually has a relationship with the number of edges in the graph. So let me kind of expose this structure to you. So watch this. And this is true for any undirected graph, and I must stress that this result also generalizes over multigraphs. For any undirected graph, the following is true. If I add up all of the degrees over all the vertices, so I'll write this with a fancy sigma notation that says, hey, look, for each one of the vertices, so for each vertex in the set of vertices, so this means n, so I'm saying for each vertex in the set of vertices, I'm going to add up the following quantities. So I'm going to sum over, so imagine I went through each one of these vertices, I got their degree, and I wanted to add them all together and throw them in one bin. That's what this represents when the sum is being used. It's summing over the following quantities for each vertex. It's getting the degrees, it's collecting them up in one big bin. This is the sum of all of them. This is exactly equal to 2 times the number of edges in the graph. So let's return back to what I was telling you about when we talked about our story about people shaking hands. Okay. If I were to ask how many handshakes happened in total of all the party members overall, so I ask each one of them and ask, okay, how many handshakes did you have? Well, let's think about this. Let's think about it. From the perspective of A, they shook E's hand, F's hand, C's hand, and B's hand, right? If you asked any one of them, how many handshakes did you partake in? They'll tell you, oh yeah, I shook hands with A. I shook hands with nobody else, right? F will say, hey, look, I shook hands with A. I also shook hands with F. And that's all F would tell you. C shook hands with A. And shook hands with D. B shook hands with A and with D. And then if you asked any D over here, you say, oh, well, I shook hands with F. And I shook hands with C. And I shook hands with B. Okay, so let's answer a question. How many handshakes happened in total if you asked each one of the people at the party? Did you see something very subtle that was happening here? Well, the total number of handshakes that truly happened is actually the number of edges. However, if you asked each party member how many handshakes they had from their perspective, let's think about it. When I asked A, I counted E. When I asked E, I counted A again. Do you see that? So notice I'm doing something that is a common counting trick called double counting. So notice that I am actually double counting each one of the edges. Do you see how a double count can lead to 2 times the number of edges? If I were to be some arbiter outside of this whole party, counting how many times truly, how many handshakes happened, they'd tell you this number of edges. But because each handshake requires 2 people, in this sense, it's you double count it. So hopefully everybody sees that. So let's write out the proof. So this is the argument I was telling you that you can try on your niece or nephew or anybody else. If you want to try out this argument with somebody and ask them how many handshakes happened in total, and you asked everyone at the party and you collect them all up in a bin, they tell you it's actually twice the true number of handshakes that actually happened. So by definition, the degree of a vertex is the number of edges incident on a vertex V of the set of vertices, right? So remember that's important. Then what happens? Well, we need to kind of frame this into an actual argument, right? Just saying that, oh yeah, I crossed the line twice, the edge twice, isn't really very seductive as a mathematical argument. So let's do that. So every edge is incident, right? Remember that's that incident concept, is incident on two vertices. Incident on two vertices. So by double counting, every edge is counted twice in the sum, the sum over each one of the vertices of their degrees. That's the end of the proof. It's very simple. Piece of cake, right? So it's actually one of the easiest proofs that I usually can show somebody. So the whole idea is if you're not convinced by this argument, what you do is you just simply walk through the reasoning we did here. So notice that every time you pick one of these edges up, each one has two endpoints, right? So if you count the amount of degree that gets contributed when I look at each one of its endpoints, it contributes a value of 2 towards the sum. So everybody see that? Very cute. Now, I mentioned as a remark that this also generalizes to multigraphs. That includes when there's self-loops present. One thing I need to point out is that a common convention is that if you have a self-loop contributes 2 to the degree of a vertex. If you accept this, where you can imagine you add a given vertex and you look at my two endpoints. Well, from one endpoint, it's the same one, right? But from the other endpoint, it's the same one. So if you actually think about it, it's okay, well, I'm really incident on myself, but at the same time, I'm also myself. So if you accept this convention, this argument can be easily generalized. So notice here that it's incident on two vertices. Notice I didn't say anything about them being distinct either. So if you accept this, this proof also generalizes to multigraphs. Because there's nothing saying that if you have parallel edges in the graph, that it changes anything about what we just said here, because it's the same idea. You'll just have two parallel edges. That means the party members just shook hands multiple times. So if I pick two party members, they would just tell you, hey, look, I shook this guy's hand twice. So one thing also I want to point out for the sake of completeness is that you can also argue that this handshaking lemma also applies in the sense of directed graphs. What you can say there is actually that the sum of the in degrees is equal to the sum of the out degrees. So meaning the arrows pointing in, if I count up all of those, and I count up all of the ones going in so I count all the ones going out, going in, they should equal the number of arcs in the graph. Sorry, I'm getting very excited. So that's a remark I'll give you here. Now, I want to bring this up into another sense here. Ultimately, by the end of this part here, I'm trying to address one question. If I give you a simple graph, what's the maximum number of edges it can have? And the answer will be given to us by a complete graph. So what is a complete graph? So a complete graph on n vertices which often in the literature is denoted as follows. It's denoted with a capital K with a subscript n, is an undirected graph. It's an undirected graph where every vertex is adjacent to every other vertex. So I thought I'll give you some examples of what these would look like for given numbers of vertices. So you can start off with just having one vertex. So this is the complete graph on one vertex, just a single vertex. The complete graph on two vertices just looks like this. Looks kind of like a little tiny dumbbell. Just I pick it up. Do some weights with these. So I got K2 here. What would this be? So if I give you three vertices, well, that's K3, right? And we actually had another name for K3. K3 is also known as a triangle, or a triangle graph. And also you can have K4. So there's four vertices. Each vertex is adjacent to every other vertex in the graph. So I have K4. Like I said previously, by the way, you can also draw these graphs somewhat differently, right? Like it didn't matter that this vertex was right here, right? It could have been drawn over here. Likewise, I could have easily taken this vertex, drawn it out over here, and gotten something else like this. So notice that this is actually no different than the following. So notice I have four vertices. Every vertex is adjacent to every other vertex. But notice it's still the same graph. So more generally, you can take to build any one complete graph, you just simply start off with, say, your first vertex, second vertex, you connect all the vertices. So notice it's like K1 going to K2. I introduce another vertex, you get K3. I introduce another vertex. I get K4. I believe I got all of them. 1, 2, 3, 1, 2, 3. One way you can check, by the way, is if you notice that the number of incident edges, the degree of all of these vertices will be exactly n minus 1, where n is the number of vertices. So if you see 3 always going out of these, then you're all good. Then you can keep going with this. So you can keep... So for an arbitrary Kn, you just keep doing this process. The point is that if you ask how many edges the complete graph has, you get something interesting. That all comes back to the degree of a vertex. How many edges does Kn have? So let's look at each one of the vertices then. Let's look at the degrees of those vertices. Because if you want to ask a question of how many edges there are, well, the handshaking lemma gives us information about that, right? If we sum up all the degrees, it's exactly equal to 2 times the number of edges. So we actually get an important ingredient for finding out how many edges there are. So let's think about it. So for every vertex I'm just going to go through each one of the vertices, just like my picture over here. 3 all the way up to n. Vertex Vi is adjacent to n minus 1 other vertices, right? But what does that mean? It means that the degree of each vertex is exactly equal to n minus 1, right? So you can come at this, answer this question through a couple of different means. In the notes, I'm going to show you how you do with double counting, which is just going to be the same argument I gave over here. But notice very quickly that, okay, well, if the sum of the degrees the sum of the degrees for all the vertices in the complete graph on n vertices is equal to n minus 1, then it's simply this. Well, for each vertex, well, what's each vertex? Well, each of them has a name, right? Vertex 1, vertex 2, vertex 3, there's exactly n of them. So I'm going to sum over from I is equal to 1 to n, because I've used these names over here. Keep in mind that it doesn't matter, it's just the thing is that there's exactly n of them. Each one of these is n minus 1. But what is this? Well, I do this n times, right? So I'm collecting n minus 1 up into a bucket, and I do this n times, right? So suppose I have a bucket here. This is n minus 1. I put it in the bucket. I would do this exactly n times. So if I have n minus 1 and I do this n times, how much should I have in total then? Well, it's n, I do it n times, so I add n minus 1 n times, so I have n times n minus 1. But the handshaking lemma tells you the following information. So by the handshaking lemma, sorry, my writing is just melting here. By the handshaking lemma, that would mean that n times n minus 1 is exactly equal to 2 times the number of edges. Well, if you can remember back, how do you do algebra here? You can divide both sides of this equation by 2. So this is no different than me writing that m is equal to n times n minus 1 over 2. So I'm going to divide 2 on both sides of this equation, and thus we get the number of edges. So another way you can derive this is through the same kind of double counting we just did over here. So that answers our question of how many edges there are in a complete graph. Very fascinating. So as a consequence, notice that for any simple graph, you can't have more edges than this. So that means that if you wanted to answer the question of how many edges can there be in a graph, the complete graph gives you that answer. So let's talk about that. Okay, so anyways, so here's a theorem for you. So for any undirected graph, so remember, I'm presuming that it's simple. The number of edges is at most, so it's less than or equals to n times n minus 1 over 2, which, if you know your big O notation, this is big O of n squared. So you can actually answer a very similar question for directed graphs. So do you notice that earlier on when I was talking about graph types, I talked about how you could take any undirected graph, turn it into a directed graph. Did you notice that I could just simply replace each undirected edge with 2 directed edges, right? So notice that you get twice as many edges, but they're all directed edges. So notice that you would just drop this 2 here. So the divided by 2 goes away because we're not double counting anymore. They literally are there. So you can also say in that case that the maximum number of directed edges is big O of n squared. Fascinating, right? So isn't that neat? So you can see that how we can use simple things like the handshaking lemma to help us argue things like the maximum number of edges that could be in a graph.